Hello, good evening. Can you guys hear me okay? Hello, are you guys able to hear me? Or no, no sound? All right, loud and clear. All right, thank you very much. Good evening, everybody. Welcome to another edition of Even Learning. For the past few weeks, I had a break, so we're restarting now. Okay, so for our first, for our first uh, topic for today, we're going to learn about AHU, pressure drop calculation, and condensate drain calculation. Uh, Let me share you my screen. All right. Okay. So we're talking about ACMV fundamentals again. So these are the fundamental things that we need to learn with regards to ACMV design. Yes, it is recorded. However, it's not broadcasting on Facebook Live. I don't know why, but I'm having trouble. It's not logging in at my Facebook account. But yes, the session is being recorded. Oops. Give me a minute. All right. Okay. So now we're talking about ACMV fundamentals. We're going to talk about air handling units, fan pressure drop calculation, and condensate drain calculation. I am your host. I'm Donnie Gabriel. I'm a professional mechanical engineer specializing in ACMV. So for those who don't know me, I'm from the Philippines. I graduated at Mapua Institute of Technology way back 2001. I recently got my MBA last year from AMA University. I started my career with RJ Calco and Partners and moved here in Singapore 2009, and I've been working here ever since. Been working as a ACMV expert. So for any questions, any comments, you can reach me at my email at evenlearning.sg@gmail.com, or you can message me, WhatsApp me through my mobile number. So for tonight, we are going to learn two things: pressure drop calculation and condensate drain flow calculation. As part of the condensate drain flow calculation, you will also see condensate drain pipe sizing and the U-trap calculation. So I see our participants now. We have a lot of participants, and I could see, I could see a lot of participants now. We're 10 of us right now. Okay. So first, pressure drop calculation. Air handling unit. What is an air handling unit? Air handling unit is an equipment encased in an assembly to perform one or more functions of distributing, cleaning, cooling, heating, humidifying, and dehumidifying, and mixing of air. So at the heart of this AHU is your fan. So we're going to size up now your fan and size up the pressure required for the fan. We're going to calculate the external only. So let me repeat. We're going to calculate the external static pressure or the external pressure drop for the air handling unit. The internal pressure drop will be dependent on the manufacturer. So when you give your requirements to the manufacturer, it is assumed or it is understood that the pressure that you are giving them or the pressure required is an external static pressure loss. The internal pressure loss will be calculated by your manufacturer and added accordingly to the size of the fan. Okay, so clear, huh? What we're going to calculate is the external static pressure. Okay, Previously, a few weeks back, few months back, we had an ACMV series. So we're going to use one of the examples there for our examples tonight. So first, we're going to assume all these heat load are already calculated. If you are interested in learning how we got this uh, heat loads for the room, you can watch the overview of heat load calculation. The link for the YouTube link is posted there on the screen. We're just going to pass through for it today. For the flow rate, for the airflow rate for each area, you can also view the past trainings for mechanical ventilation calculation. Same link from the YouTube. And last, the duct design, or how we come up with this duct layout. It can also be seen on the YouTube link there on the corner. Okay. So we're going to assume we're going to proceed with these data, with these numbers already calculated, already into. We were not going to recalculate them again. So again, these are the heat loads for the area. These are the flow rates for the area. And this is our proposed duct design. So this is the supply. We're going to show you the return also. But if you want, or if you're interested in knowing how we got these things, you can watch the YouTube playlist at the corner of the screen. Okay. So first, again, going to have a pressure drop calculation. This is our proposed office layout. This is our example office layout. This is grid. This is a ceiling grid, 1,200 by 600 mm, just to give us an indication of the scale of the area, to give us an idea how big and how far our calculation is, because we're going to measure distances. And this is our proposed duct layout. So you can see the difference between the previous one to our duct layout now is there's the return air duct highlighted by the color pink on your screen. Okay. So there's supply air duct, which is color white, and the return air duct, which is color pink. These are the data, or these are the flow rates that we have calculated before. So right now we have a few areas. We have the conference room here on the side. Oops, sorry. Let me get my, oops, sorry. Let me do that again. Oops, again. There. So here we have our conference room. Okay, and this is our office, pantry, lobby, and our main office area. So for each area, we have calculated the airflow rate for each area and the airflow rate for each diffusers. Okay, this is pre-calculated already. Okay. So we're going to define now the duct accessories that are included in our duct design. First, of course, the blue ones are the supply air grill or the supply air diffusers. Okay. The pink one are the return air grills or return air diffusers. We put there with VCD or with volume control damper. There's also VCDs there on the main sub branches here to help us balance, so it will be easier to balance when the system is installed. And outside the office, we put fire dampers, assuming that our AHU room is just beside the office, so we put fire dampers. This one is a VCD or volume control damper, and this one is our duct silencer, so that the noise from the air handling unit doesn't transfer to the office. So you can also see the type of branch duct that we are using. We're using the shoe type. Okay. Later, going to show you what are the different types of branch duct and how we're going to calculate for each of the type pressure drop for each type of branch duct. And based on based on these numbers, based on these flow rates, and based on these accessories, we're able to size up the ducting. Okay, so each area we already provided the size and the flow rate on the ducts on that particular member on that particular point of the duct. Okay, again, for those who are interested in how we got this duct size, you can watch the previous training flashed earlier. So those who are here, I will provide this slides so you'll get those data, or you will get those information where you can watch those previous trainings. Okay, so how are we going to now? How are we going? Now we have our duct accessories. We also have our flow rates. Now we have our duct size based on those flow rates. Okay, so we're going to determine the pressure drop for the air handling unit. When we get the pressure drop for the air handling unit, we typically get the longest run or the farthest run, because usually the farthest run is the highest pressure drop experienced on the system. So the pressure drop, we consider both the return and the supply duct. So we consider this point in the return duct to be the farthest run. So the air will be sucked from here, travel here, go down, and then go to the AHU. And in the AHU, the air will be cooled down, and then it will be supplied. The air will travel here all the way to the corner, the farthest corner of the conference room. So that will be our estimated farthest run or estimated pressure drop. From here, from point 1, we call this a point 1, point 2, point 3, point 4, point 5, point 6, point 7, 8, 9, 10, 11, 12. These points are for user reference. So it doesn't necessarily have to be here, doesn't necessarily have to be here. Each point, it's up to you to decide where you want to put the point, as long as the purpose of it is to help you be aware and to help you organize your thoughts. So it won't be messy. Later, we would see it won't be messy if you have your points defined as it is. It doesn't matter where you define your point, as long as you can follow it, as long as you can keep track of each of the items there. Okay. So I will escape here. I will escape from this screen first. Oops. I will show you here and here. So this is the same thing, no? This one is the same thing. I just made it smaller. And then I'll pull out my Excel sheet. There you go. When we calculate the pressure drop, we will calculate each and every item or each and every accessory on the duct system. This is our pressure drop, our layout earlier. Okay. You guys can still see my screen even though it's smaller. You can still see the drawing and my Excel sheet. Can see pa, can see. Oops. All right. Can see, huh? All right. So we will go with point 1 there. Point 1. So I mark this as point 1, this return air grill as point 1. So I put here point 1, type of fitting, egg crate or return air grill. For this egg crate, I know the flow rate of this one to be this much. The size, this much. So this one area, easy to calculate. This one times this one equals this area. Velocity is area, flow rate divided by area, you will get the velocity. K factor. Where do we get this K factor? This is the meat of your pressure drop calculation, your K factors. You can see the formula. There's only two types of formula, no? Factor times density times velocity divided by 2, or factor times length. It is the only two formulas that we're going to use. So where do we get this K factor? This K factor, I put the reference here. Okay. Reference is CIBSE guide figure C 4.35. And this is it. There you go. This is the CIBSE guide. There. Oops, sorry. Table C435 there. Match C435. The return air grill or the egg crate is estimated to be here. Wire mesh. Wire mesh free opening assume at 80%. 80% wire mesh. There you go. Free area ratio. Wire mesh. 80%. The K factor is 0.3. So we wrote there 0.3. Calculate using this formula, you will get the pressure drop of this much. Question? No question? Still can follow? Okay, still can follow, huh? So, once this air passes through the egg crate, it will go through this duct. This duct is a straight duct. So next item, straight duct. Flow rate still same. Size different already. The size is 300 by 200. I will show you. There. Size of the duct is 300 by 250. So we wrote there 300 by 250. Area, we can calculate length. How did we get the length? Easy. You could see from our drawing there. We can count the number of grids. 1, 2, 3, 4, 5. So from here to here is about 5 grids. One grid is about 0.6 meters. So we can assume that 0.6 times 5. 1, 2, 3, 4, 5. There you go. Length, 0.6 times 5. You get 3 meter length. So 3 meter times 0.52. Where did we get this 0.52? Okay, let me open up my duct sizer. There. All right. Again. Oops. Straight duct, we have 300 by 250. That's our duct size. So we'll write down here 300 by 250. You can see here the equivalent diameter 299.07. So we'll write 299.07. The flow rate is 239 units metric. 300 by 250 is 299.07 times flow rate of 239. There you go. Head loss for this size and this flow rate, the head loss is 0.516. So we will write there. 0.516. There. That's how we get the flow rate, the pressure drop on the straight duct. So based on the flow rate, and the duct size, you will be able to get the pressure drop, the K factor, and get the pressure drop. K factor is this one, Pascal per meter. So if this is Pascal per meter, this is how many meters. You just multiply them, you'll get the pressure drop. Next, here the air travels from here, goes to the straight duct, and then here there's a branch. There's a branch here. We call this branch as a converging branch. Now our reference is SMACNA table 14-138. Okay. SMACNA. There. Converging T. This is what we're doing now. So you can see based on this converging T, there are three parameters: the area, the flow rate, and the velocity. Area, flow rate, area, flow rate. So this is point A or point 1, A. This is point B, and this is point C. This is your main duct. So we're actually here. This is where we calculated for earlier, and then it's because of this point, the air passes through here. The air turns here. So what is the pressure drop on this point? Here's the table. The table says we need to get the flow rate ratio of QB and QC. The flow here and the flow here. What is the ratio? The flow here and the flow here. On our Excel sheet, the flow ratio is this one and this one. This is the flow, this 239 is the flow here. And the flow here is 917. So what is the ratio of this 239 and 917? There, 0.74. Okay. At 0.74, you can see here, between 0.7 and 0.8. And here it says here that we need to check which is the velocity, meters per second, 6 meters per second. Is it higher or lower than 6 meters per second? We'll double check. It's velocity lower than 6 meters per second. It's actually just 2.45. So which means we're going to take the top value. Our flow ratio is 0.74. So in between here. So we will use either 2.15 or 2.93. What I used is 2.93 because it's a higher number. We're in between 7 and 8. So I'll just use 8 just to be on the safe side. So 2.93. So converging T based on the flow ratio and the velocity of the duct on the duct. Our calculation says our flow ratio is 0.74 and our velocity is 2.65, less than 6 meters per second. In between here, I took the more safer number, 2.93. That's why it's 2.93 there. Question so far? Question? No question yet? Okay, none, still none. Okay, you still follow? All right, so so here here we have a converging T, okay, on this point. After the converging T, there's a straight duct, so from here to here, and then here another converging T. Straight converging T, straight converging T, straight converging T, straight converging T, straight converging T. Straight up to here. So how many converging T's are there? 1, 2, 3, 4. How many straight ducts? 1, 2, 3, 4, 5. Our Excel sheet, there. 1, 2, 3, 4 converging T's. 1, 2, 3, 4, 5. 5 straight ducts. So we will repeat the process as we have made earlier from this tree. So this tree has, we calculated this one, the process we calculated this one. We'll be repeating the same thing up to here, straight duct. And then VCD. So that's, now we're at 0.3 already. So we can see here on our drawing, this is our converging T at 0.2. So that's it, the first converging T, 0.2. And the VCD converging T at 0.3. So this is the one, converging T and VCD at 0.3. So this is, this 0.3 is referring to this point. So 0.1, 0.2, 0.3, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 items. So we can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 items before it reaches 0.3. Question. Question again. Still none. All right. Oops. So here, we already calculated the egg crate, we already calculated straight ducts, and we already calculated converging T. Now we will calculate a duct accessory, that's a diffuser. Okay. Diffusers. Okay. First diffuser is the VCD. VCD, this is the flow rate as we, as the air moves here, the airflow rate increases up to this point because converge, 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 converge. The airflow rate increases up to this point. At this point, the flow rate already increased to 2571. 2571, this is the duct size already. This duct size can be seen, the pressure drop for this fitting can be seen using SIBSE guide. Okay, let's go to SIBSE guide. So this is the SIBSE guide there. Under obstructions. Under obstruction, there's dampers. There you go. There's dampers, there's the butterfly damper, and there's the vane type damper. Let's assume the worst case scenario. We're using the butterfly dampers, and the flow, the K factor is 0.5. So it's easily defined, 0.5. So we put VCD, K factor, 0.5. You might notice some of our converging branches, have a negative K factor, giving our pressure drop negative. Why is that so? Let's go back to the SIBSE guide, SMACNA guide, sorry. Based on the SMACNA guide, there. Here, oops, sorry. Whoa. There. All right. So here on this converging branch, you can see the flow rate ratio, is about 0.21. The flow of here and here, the ratio is 0.21. Okay. At 0.21, it's here in between 0.2 and 0.3. SMACNA guide says the value is a negative value. That's why we got a negative K factor. Our flow rate is less than 6 meters per second. See, the velocity is of only about 3. We got the higher value, 0.3, there, 0.3, because our flow ratio is only 0.2. In between 0.2 and 0.1, we got the 0.3 K, negative 0.3 K value. Why? Because the flow here is so high, the the flow here is high and the flow here is low, that it naturally sucks the air here. That's why it's actually helping the air to transfer from this point going here. That's why the value is negative, because the ratio, the flow rate here is very high compared to here. So because of this, because of the effect of this flow rate, this high flow rate, the air is naturally sucked here, giving you a negative K value. That's why here, from here, you could see our converging branch is negative values, which means the system itself is helping to reduce the pressure drop. But it only happens on converging, or it only happens on exhaust and return ducting, not on the supply. Return and exhaust ducting only. Okay. Question pa? Any more question? All right. One more. Converging T at point 3, then straight duct. All right. Let's go back to our drawing. Converging T and straight duct. Straight all the way here at point 4. You can see at point 4. Point 4, we have a bend. We have a 90-degree bend. Okay. On the 90-degree bend, point 4 there, 90-degree bend. It says here again, SMACNA. Sorry, SIBSE guide. So we'll go back to SIBSE guide. There. Miter bends. Miter bends, you can see the one that we use in our drawing is a very nice, smooth 90-degree bend. So looking at our guide, we are using this one. So the K factor is 0.67. So we wrote there, miter bend, 0.67. So you can see here on the SIBSE guide, it also gives you options if your bend is different. For example, this square bend with vane diffusers or internal diffusers, this one also. Or this one is a square bend. It also gives you here, if you have a different angle. So if it's not 90, say 45 degree, there you go. 45 degree is 0.6 times this one. So this is your guide if you're not using 90 degree, if you're using different angles. And this is your main factor. So this one multiplied by this number, it will give you your appropriate K factor on each different angles. So this angles is this one is based on here 90-degree height and width, radius there 0.67. Where's 0.67? Oh, there's no 0.67. Oh yeah, sorry. So this one is assuming that you have 1D diameter. This miter bend is 1 degree diameter. So which means your radius here, your radius is equal to 1D, or equal to the width of your ducting. That's how you get the 0.67. If you have a different radius, you need to determine based on the height-width ratio of your ducting. Based on your height-width ratio and your radius-width ratio, you'll be able to get your K factor and then multiply by the appropriate angle of your bend. So example, our ducting is about, let's say 2. The height and the width ratio is about 2. So you'll get about around here. And then the ratio, radius and the width ratio is about 1. So here, 0.2. 0.2 times 90 degrees, 1. So your K factor is 1. Okay, so this one, if you have a different angle on your bend, this one if you have a 90-degree bend. So there, we're done with the 90-degree bend. And then we go back here. After the 90-degree bend, we have an enlarger. Enlarger. So we go back to our CPC guide. Enlarger. Here, enlargements. Our enlargement, let's say gradual enlargement, based on angle again, the angle of enlargement. So this line and this line, their angles can will determine your K factor. Let's say at 40 degree. This symbol here is if you're using circular duct. This symbol here if you're using square duct. So this is your abrupt and this is your gradual. So we're using 40 rectangular as 45. So we're using 45. So in between 40 and 50, let's use 40 at 1. So 1 times the area ratio. So we can go back here. Air enlarger, area ratio 0.75. This is the small area, this is the large area. So the difference between this, the ratio of the small area and the large area is 0.75. 0.75 is about here, 0.9. Abrupt 0.9 times factor of 1. So 0.9, 0.9. So that's how you get the K factor for enlarger, 0.9. We got it from here, 0.9 times our angle, 1. So 0.9 times 1 at squared ducting. So we can calculate here. Let's go back. So here we enlarge, we enlarge and then convergence again, converge, straight duct, converge, straight duct, converge, straight duct, converge, fire damper, volume control damper, and then air handling unit. So at 0.6 is your VCD or volume control damper. So there you go. Sorry, baliktad. This is fire damper and this is volume control damper. So fire damper, volume control damper, and modulating damper, they're all dampers. So because of they are similar, they're all dampers. We all use the same K factor of 0.5. And after that, you have your air handling unit. Again, we are only calculating the external. So the internal internal pressure drops, we don't calculate. These are the fans, the coils, the filters, and the coils, and the fan itself. These pressure drops will be given to you by your manufacturer. Same is true with your silencer. Here, the silencer we only assume at 50. This is only an assumption, but your because it's outside the air handling unit, it's part of our external pressure drop. But this external pressure drop will be given to you by your silencer manufacturer. In the meantime, we only assume it at 50. So same, from here, this point, silencer, we have a bend, then straight duct, and then fire damper. So bend, straight duct, fire damper. We already calculated each item. Straight duct, and then branch duct. So earlier, the air is going here and is being added. Air is being added to our flow. But now, air is being subtracted to the flow. So our point of interest, the air flows here. But as the air flows here, some of it are being subtracted by these air branches. So we will calculate one at a time. So this is this, even though they're opposite each other, the calculation is first here and then here, two separate calculations. So first, on this portion, air is being subtracted from here to here. So you can see here, air is being subtracted from 6972 to 6,400 liters per second. So what are we going to do now? Let's go back to our SIPSE guide. There, rectangular duct branches. Our duct branch is on this type. You can also use different types of duct branches, but our calculation shows this one. So based here, what we want to know is the velocity ratio. So the velocity of our duct is from here, there, 0.92. Previous velocity, new velocity, 0.92. At 0.92, it's between here and here. We will use 1 because we are looking at from here to here. We are not considering this portion. We are considering this portion. So B1 to B2, 0.9 here, 0.4. Duct branch, 0. Oh, no. This is supposed to be, oh yeah, 0.8 because it's 0.92. 0.92 here, 8 and this one. So we get the higher amount, 0.09. There. So again, similar way, similar principle, straight duct, branch, straight duct, branch, straight duct, branch. Straight duct, branch, and here at 0.9 and larger. Question before I continue? Wala naman? No question? Okay, almost done. And reducer, sorry. So this point is reducer at 0.9. Reducer at 0.9. Reducer at 0.9 is here. There. Similar to earlier calculation, enlargement, this one is contraction. Contraction also same based on your angle. Based on your angle, let's say 45, you could see here, A or B, this way or this way. I'm this way. We're going this type of reducer at 45 degrees, 0.2. So you can see here, reducer 0.2. And as you continue, on each item and each duct accessories, will be able to completely calculate the pressure drop for the system. So the summation of all those systems will lead you to a total of about 327 times 10% safety factor, about 360. So which means this layout from this point going to your AHU and from AHU going to the farthest point, number 12, is about 360 Pascal. Question? None? No question yet? Okay, let's continue. Condensate flow. So, assuming earlier we have a 73 point total of 74.3 kilowatts for the whole area. Our design parameters is 21 degrees Celsius at 50% RH. Our fresh air is about 18%. Okay. How are we going to calculate the condensate drain? We're going to look at the psychrometric chart. Psychrometric chart, similar to earlier, if you want to know detailed explanation or overview of the psychrometric chart, you can search our, you can see our YouTube channel as flashed earlier. Okay. So here, outside condition, oh sorry, outside condition, this is design condition for Singapore. This is our design condition. So the outside air, 18% will be mixed with 82% of this condition. When these two air mixes, the resulting is here. As it's this air or this air condition will be the one going through the coil based on the psychrometric chart. The dew point that we're going to have is this much. This is our dew point. So the difference between these two, the humidity ratio of these 2 points, one is 0.78, one is 7.14, is the amount of moisture or amount of condensate that we're going to expect or extract in the system. So how are we going to calculate that? We calculate it using this formula where Q is the condensate drain flow rate, M is the air flow rate or the total supply rate, times the difference in humidity ratio multiplied by the density of air and water. Okay, so our total is 92.72 liters per second. So you can see here again, there, 9672 liters per second, the total flow rate. So based on this number, we're able to calculate this one. Based on this number, 9.78, 7.14, 9.78, 7.14, we're able to calculate the difference in humidity ratio. This humidity ratio is expressed in grams of water per kilogram of air. So this one, this liters per second multiplied by the density of air will give you kilograms of air. And this gram of water multiplied by the density of water will give you liters of water. So that's why our resulting equation is in liters per minute. So the seconds just convert to minutes. So 1.32 liters per minute. Based on this 1.32 liters per minute, we're able to size up our condensate drain. So again, this one is based on 74.3 kilowatt. There you go. 74.3 kilowatt. The condensate drain piping is minimum at 25. You can see minimum at 25. Sometimes you got some people will calculate this at 25 or 15 degree, 15 mm pipe. But no, the minimum is 25. Here in Singapore, the minimum is 32. Whatever AHU or whatever FCU size that you have, the minimum is 32 mm. This one is for maintenance purposes, so it's easier for them to maintain. But some areas still accepts 25. So based on your kilowatt, you'll be able to size up the size of your condensate drain pipe. Be careful when you size up your condensate drain pipe because you have your U-trap. What is a U-trap? So this U-trap is the one that's what do you call this? Intentional stagnation of water so that the fumes or the gases from your drain doesn't go back to your AHU, doesn't go back to your airstream, doesn't contaminate your air. So this U-trap, because of the pressure drop of the fan, affects the size of this U-trap. The pipe itself is not affected. It doesn't matter what size. What matters is the height of the water. Okay, there's two types, no? The first type is your draw-through fan. Based on your draw-through, water is actually being sucked up. That's why we need to maintain a certain height so that even though this fan is running, there's negative pressure being created here. There's ample height of water to seal up this U-trap. Okay? Assuming the blue color is your water and this one is clear. It's easy. Earlier, we already calculated the fan static pressure. So assuming the total fan static pressure is the one that we have calculated, we could just simply convert this pressure into inch of water. That's how easy it is to know the height requirement of your U-trap. So 250 Pascal per inch of water. A fan generating 250 Pascal of pressure affects water by 1 inch. So this fan will experience at least a 1.5 inch raising of water. But sometimes the fan is a blow through. So this is a draw through configuration where the fan is creating a negative pressure. But what about fans creating positive pressure? It's called a blow through. So here is the same thing, but you could see that the height is on the opposite side. So here, the height of the water is on this side, but here, the height of the water is on this side. This portion, no, this portion, and this portion doesn't really matter. This one is based on your preference. As long as there's a U here, and as long as it's a little bit higher, it doesn't matter how high you want it to be. As long as this height is maintained. Right. Question? Any question? Question some more? If not, that concludes our session for tonight. If you have any questions, if you have, that concludes our session for tonight. If you have any questions, you can find me at evenlearning.sg@gmail.com. Let's see. Magandang question to. This is a good question. For COVID, what are the possible treatment necessary for return? Good question. Wow. One treatment that we can do on the return side is to provide ultraviolet rays or ultraviolet germicidal ano ulit yun? Again, let me double check. UVGI. That's the acronym UVGI. UVGI. Ultraviolet germicidal irradiation. There you go. So that's one way that we can do. We can put it on the return side. We could also put inside the AHU or within the ducting, either on the return side or in the supply side. That's actually our topic for next week. Next week, we will have our guest, Miss Joanna, telling us more about UVGI. Okay, so for those who are interested, for next week, UVGI by Miss Joanna, also here at Even Learning. Slides, PDF, Excel, to share? Yes, of course. For those who have registered, as usual, we will provide you your certificates if you have requested. And for those who didn't request it, I will still provide you your slides, the Excel sheet that we have used, and the PDF references that we have used for tonight. Those will be given to you as long as you have registered. And also the recording of this video will be uploaded at YouTube and at Facebook. I'm sorry, the Facebook Live didn't work, but this recording will be uploaded in YouTube and in Facebook. So the link will also be provided. Do we have a topic regarding VRV and split type air conditioning? Coming soon. Coming soon. We will try to accommodate your request. Coming soon. I'm looking for resource person, somebody more familiar and more expert than me on this subject. How about the exhaust and fresh air static pressure? Same approach? Yes, same approach for exhaust and fresh air. Doesn't matter whether you're using exhaust or you're using fresh air, makeup air. It's the same principle, same approach. For SIBSE and SMAC na copy, I will send to you. The one that we have used today, the SIBSE and SMAC na, I will send to you. I will give you a copy. Any more? Any more question? If there's no more question, I'm glad that you guys are able to participate with us tonight, and I'm also glad that you are safe. So I'll see you guys next week. Keep safe. See you again soon. Thank you.